This presentation will give an overview of fault management. It was prompted by the crash of the Hakuto-R lunar lander. First, we'll provide a simple example just to get started.
For fault management, you break it up in several parts. Just recognizing that you have a problem at all, that's fault detection. Then you have fault diagnosis, saying, well, what is a specific fault? Two different things. And then what do you do about it? So there's at least three different things there. I just have a real simple example here. Suppose you're transferring propellant on your launch site. This would be like a Starship or something. You got methane, you got it in a tank on site, and you're transferring fuel to put it on the rocket. Now, suppose you measure it. Either you're measuring flow rates, or maybe more likely, you measure how much the one tank level went down in a period of time, and you compare that to how much it went up in the rocket, calculate the volumes. But either way, you have an estimate of how much flow left this launch site and how much went into the rocket. And what if they differ? So in my example here, we're saying, okay, what if you measured 100 going out, and what if the rocket only measured 96 coming in? Well, what's the situation here? Was there a leak? Maybe you lost. It looks like you lost 4, units or whatever it is, or maybe you got a sensor problem. Maybe one of them is wrong. Maybe, but which one? You don't have enough information there to tell. Or what if you have a leak and a sensor problem? It's possible to have multiple failures. 2 failures rarely happen at exactly the same time, but especially in missions that last for years, there's a good bet that something has already failed, and then this is going to be the second or third failure, and all those things are possible. Now, the other possibility is, well, these are just noisy measurements. Maybe it's not that unusual to be off by 4. So for flow instrumentation, actually, that wouldn't be that surprising. For level instrumentation, that's usually a lot more accurate, but you have to understand what the sensors are. So all this kind of stuff goes into actually managing faults properly, and then deciding what to do. Which one do you believe? Do you just say, well, okay, we assume there's not a leak and we probably transferred 98, just all those things are all possible, but these are the kind of problems people face.
Let's talk about the general field of fault management. Getting down to basics, what is a fault? We didn't write it here, but a fault is simply a problem, usually thought of as a root cause that leads to all kinds of bad symptoms. So for any problem, you could always ask, well, what could cause that? And then you could ask, well, what could cause that? And so on. You stop looking upstream like that when you reach the point where the fault is identified accurately enough that it can be repaired, or maybe you reach an organizational boundary where it's someone else's problem. For instance, when you conclude that some part has failed, you don't need to ask, well, where did that part manufacturer fail in their production? You stop at that point. You replace the part, or you learn to cope with it if you don't have a way to repair it. So fault management has general activities that apply to every industry. Not only are the activities similar, but in many cases the spacecraft equipment runs or fails about the same as their earthbound counterparts. For instance, rockets have tanks, valves, pipes, pumps, and sensors like many industrial sites. Rockets and satellites have wiring and electronic equipment just like their earthbound counterparts. All spacecraft have communications, and the behavior of link networks of communication satellites, like Starlink or Iridium, they fit nicely into fault management, which is really highly developed as part of network management. The general activities are listed here, sequenced in time from when any particular fault occurs. And the first step here is detecting the fault. The fault might be in the sensors or it might be in equipment. When fault detection is automated, it usually is done just using routine monitoring of sensors. Now, isolation, or just diagnosis, is the next step. What are the possible root causes of this fault you just detected? Now, that might just use the monitored sensors that were used in fault detection, but it may additionally include much more active testing that you don't normally do. Another part of this usually is including the impact of failure, that is, assessing or predicting what this failure will lead to, because that helps you prioritize what you have to do if you have more than one fault. Next, you get into fault mitigation. Fault mitigation means do what we have to keep on operating. That could include before any repairs can be done, or even during the repairs, if repair is even possible. As an example of fault mitigation, for a sensor failure, that might include using an alternate method of estimating altitude in the case of Hakuto-R, in the case of a lunar lander. Perhaps the alternate method isn't as accurate, but you can limp along better than going without it. The next step is repair, if that's possible. Even for unmanned missions, repair is sometimes possible. This has included things like rotating a spacecraft to get it heated up on a particular side to free up parts based on differential expansion. It could include introducing vibrations or unusual force to get something unstuck, as has happened with solar panels on multiple spacecraft. A common one is rebooting a computer. That's kind of common because memory might get corrupted, and this is a way to clear that memory. Or there could just be an unknown bug. Purpose is to clear the memory again and start fresh. Preventing recurrence means noticing repeated failures and then correcting via operations or by design. It could apply to within the same mission, if it's something that can be repaired anyway, and certainly for future missions. So it's not really considered part of everyone's fault management, but it is an important part of continuing improvement. You have to have a cycle where you analyze what went wrong, you redesign something, you implement it, and you monitor the success. If the cycle starts again, you go through the cycle again when the failure recurs. But the general idea is continuous improvement. There are some important issues to deal with in fault management. One is anytime you're dealing with sensors at all, you probably have some signal processing you need to do to reduce the impact of noise. And looking at the graph to the right here of a variable over time, this is a sensor reading, and you have all kinds of noise in there. The result of that could be false alarms, which are misleading and dangerous, and an annoyance to people if nothing else. Or you might actually miss a fault because of noise. So you have to deal with that one way or another. And there's even multiple kinds of noise. For instance, the center of this particular graph, you see some what you call high frequency noise. It rapidly varies very, very fast. And a lot of times you can filter out quite a bit of that. Another kind of noise is a spike, which you see more toward the left-hand side here. And then around that, there was high frequency noise, but it was much less obtrusive. So noise has to be dealt with. It takes signal processing and filtering of one type or another to take care of that. The next thing is event filtering, which really includes alarms or messages of any kind. You're not really dealing with sensors anymore, even in your typical physical systems. You have a lot of smart instruments, you have a lot of subsystems, each of which have their own computer. They probably have their own built-in tests. That's actually kind of a big thing in the aerospace world. So they generate messages rather than just generating values like a sensor would value. And the problem with them is they can be repetitive. So you need to many times suppress the repetitive ones, which are just the same thing over and over again. Or you might try to correlate from multiple messages. The modern systems, any one subsystem might generate thousands, literally 1,000 possible messages associated with it. And you might do things like event correlation, where you just say, okay, if I've got 5 different messages from the same subsystem, I'm going to conclude that that subsystem is bad. And you go from there. Related to this are user interfaces. That includes alarms, which typically are messages or events, like we were just talking about, and displays. Anytime where humans are involved, you have to worry about the user interface. That means presenting a concise analysis rather than just having a flood of messages, most of which are indirectly implying the same fault, but there might be dozens or hundreds of messages that come out as a result, either over different objects or even over the same one but different times. Next thing is planning for tests. As I said before, you typically detect faults just by monitoring routine sensor data. But there's a lot of other kinds of active testing that might be disruptive. It's not just monitoring the passive sensors. But you need to do that when you're doing the diagnosis, trying to figure out what went wrong. Examples. You might fire a thruster to see what kind of response you get. Did a sensor notice it? Did the craft move? Did 5 other sensors verify that something happened? Rebooting a subsystem. That's actually a common one on spacecraft and, well, every kind of equipment, really. Because memory gets corrupted or bugs corrupt the memory in one way or another, rebooting takes care of things. If you reboot, and the problem goes away, then that tells you, okay, you had a problem with either a computer bug or maybe you had a radiation-induced memory problem. But either way, you've identified it. It's not just a fix. It also is diagnostic information. Anytime you have a network of communications, you're going to have some kind of a ping, basically sending out a signal saying, are you there? And you get a response. And from that, you can check for communications failures. You might not do that on a regular basis with everything in the network, but when troubleshooting, you might issue more of these. And if a human has to get involved, a human might measure a voltage on a circuit board. There wouldn't be a sensor for any particular point on the circuit board, but a person with a voltmeter can certainly go and do that. Now, the thing about tests is they take time and they may consume limited resources. The example of firing a thruster, not something you're going to do routinely because you're going to use up all that precious propellant that you have. So you have to plan these things carefully, and ultimately, planning when to run a test is definitely a part of the overall process. And last, but very important also, is when you design your system, you really want to make sure that you have enough redundancy in there. And that means having enough sensors or providing for enough analysis. If you have two sensors that effectively measure the same thing, but they're different types, like we were comparing a level in a tank, compare that to some kind of a mass measurement. Ultimately, they're telling you the same information, but you need to take advantage of that relationship. You need to plan ahead for all that. So that design is important. Next, we'll start talking about ways you can detect faults, and we'll start with a single sensor just by itself. What can you really tell from one sensor? The real answer is not a whole lot without cross-checking, but there are things you can do. So there are these tests, most of which talk about how the values change over time. First question is, are the values even physically possible? An example of that would be, suppose you're measuring a temperature on a radiator. You got a spacecraft and you're trying to radiate some heat. That temperature on the radiator cannot be colder than the outside temperature. That thermodynamically just can't happen. So that's an example of a check you might do. A second thing is looking for rapid changes that are maybe too fast. You ask the question, how fast can a physical system change? Now, this, of course, was one of the problems they had with the Hakuto-R lunar lander. They thought that there were limits to how fast a spacecraft could change its position with looking at an altimeter, but they forgot that on the ground they can change arbitrarily fast. So you can be wrong on these kind of things, but it is in general a method of looking for possible problems with a sensor. If it changes too fast, maybe it's wrong. Another example is flatline, that is, the value doesn't change. Or, you would actually do a statistical test over time saying, has it remained within some very, very small standard deviation of a particular value? Because in general, usually when things stay that constant, it's not realistic. Probably the sensor failed. Not always. And the other course, of course, the other case is there's a special case of a flat line, and that's that many sensors have a maximum or a minimum value. They can't read anything higher than a certain value or lower than a certain value. That's called saturation. If you're stuck at one of those values, it doesn't really mean the sensor has failed, but it means that the conditions that you're measuring are outside the range of the instrument. So it's a different kind of a failure, but it is a failure. Another issue is learning to ignore spikes in the value. We showed that in this graph to the right-hand side here. Toward the left, there's a spike, a sudden rapid change in value, but then it comes back fairly quickly to the value it was at before. This kind of noise is pretty common in certain cases. For instance, if you have electrical motors, when they start up or change speed rapidly, you may get a spike like that. So it's not unusual in systems where the sensors themselves or the wires are going anywhere near an electrical motor. You have to watch out for those kind of spiky kind of noises. So you don't declare the sensor has failed in that case. Rather, you just ignore the values for a short period of time until you're, one, either back to normal, or two, you're sure that the rapid change was in fact true. Another example when these things can happen is in the case of a spacecraft, you got things like solar flares leading to huge surges in electromagnetic effects, and that can also induce a lot of electrical noise, some of which can be spikes like that. Now, a word of warning about all these things. These tests are really simple, but they do require tuning, and that's based on the sensor's typical accuracy and their typical noise, and also the process being measured. So, for instance, looking at that graph on the right-hand side where you had a lot of high-frequency noise up in the center of the graph there, if that's normal, you better be careful that you recognize that a rapid change over a very high frequency is actually okay. Now, you can knock a lot of that out with low-pass filtering. It can be done. However, you have to be aware that the heavier the filter, you dampen out more and more of that high-frequency noise, but you also slow down the response of your diagnostic system. So The little graph that's shown below the noisy graph shows you an example of a typical kind of a filter called an exponential filter, a first order filter. And it shows you the response to a step change. So in the above graph, there was a change. It went from one value, the underlying value went from one to another, and there's a bunch of high frequency noise. And the problem is when you run it through a filter, you might end up with the graph looking like this magenta line here, where it kind of goes up gradually. So yes, it knocks out the noise, but on the other hand, it also really slows down the response of your test. So you have to be aware of all that. And in general, you have to also think about the ways that sensors fail. There's the high frequency noise, and that's just noise you can filter out. But even if you filter it heavily, there may be bias errors, that is, an offset that's constantly reading either too high or too low. Anyway, as soon as you start introducing filtering like this, you've introduced a tuning parameter. How heavy is your filtering? And all that stuff is introducing more complexity, and it delays your diagnosis. Some other comments I should make here is that we use the word sensor rather loosely. It could actually be some kind of calculated value, typically done on monitoring something over time. For instance, some kind of a frequency analysis. People do Fourier analysis and find out that you have a lot of noise or power at a certain frequency, and you look for that. You may look at the standard deviation over some time period as an example, looking for noise. Sometimes when you get this rapid high frequency noise, it actually indicates a process problem. A classic example of that would be, say you've got a fuel flow and just going into the pump, the pressure could be fairly low, and it's actually quite possible that you'll end up getting vaporization at that point. You get a bunch of air bubble, well, a bunch of bubbles of whatever the fluid is, the gas phase. And when you start getting that, the measurements themselves get very noisy, and that also has a bad effect on the downstream pump or compressor. It causes it to vibrate quite a bit. And you may get this. So sometimes having a high level of noise is in fact a symptom, and you'll take that as a form of measurement. Not the sensor value itself, but just the fact that it looks like it's being noisy, maybe reflecting something that changed in the process. So in general, you might look at performance over a time period. You look at efficiency, and even in your house, you look at things like efficiency of your air conditioner, and you decide if it's really dropped off over time. Well, maybe there's a problem. So all of these things are things you can do with a single sensor. Looking at the values, looking at rapid changes or flat lines, looking at spikes, looking at noise. Things start getting better when you can add duplicate sensors. And by duplicate sensors, I mean two sensors that are measuring the exact same physical quantity. So in the example below, we have something pretty much approximating that. This is a schematic showing a pump going through a valve and having three flow meters measure the same flow. And as long as you assume that a leak is very unlikely, these are essentially the same situation of three measurements of exactly the same physical quantity. So it's the simplest form of redundancy. When you duplicate your sensors, you are adding redundancy. And redundancy is something you really need for really critical functions like landing. Now, with the duplicate sensors, you can detect faults. At least you realize, because sensors give different readings, that something's wrong. You might be able to diagnose, depending on how many you have, you might be able to diagnose the problem. And also, as a side benefit, you might be able to improve your normal operation. Typically, if you average the value of a couple identical sensors, you get a better estimate of what you're trying to measure. Because the answer, in general, when things are truly random, some of the errors cancel each other out. So averages always come out better. So how do you tell what's going on? Well, you look for deviations between the duplicate values. You look to exceed some kind of a threshold. Again, a tuning parameter. You have to enter that based on your sense of what the normal noises are and so on. You probably do this after you've done your spike filtering and really high frequency noise filtering. So it takes two sensors to even detect a fault. You can just say they're different, something's going on. It takes three really to decide on which one to discard. So for instance, with three sensors, like the example below, you might take the average of the three and then throw away the one that's the farthest from the average. So in the example on the left, you have two readings of 100 and one of 112. Well, that one's sort of an outlier, so you just throw that one out and you average the other two and you have 100. The same thing could be true on the one to the right, where in this case the outlier is the 88. The only thing here is if you also are going to entertain the possibility of a leak, it is possible that the value dropped off in that third sensor because you had a leak in between the second and third sensor. So it depends on your belief in how likely a leak really is. If it's heavy duty pipe, it's not that likely. That's something to consider. So this could be treated as a simple model as well. I mean, you're saying two sensors measure the same physical quantity. It could be a situation like this where your model is flow is constant through an entire piece of piping. And of course, as I said, it does require tuning based on the sensor's typical accuracy and noise. We looked at what were in effect simple mathematical models. Two measurements should be equal. A variation on that is when two sensors measure different types of things, like pressure and temperature, but they are related by an equation. The example shown here is a curve relating pressure to the temperature of boiling water. At sea level, water boils at 100 degrees centigrade, 212 Fahrenheit. But up in the mountains, the atmospheric pressure is lower, so the water boils at a lower temperature. So here, y is the temperature, x is the pressure. So y is a function of x, or just written y equal f of x. So other examples of this include pressure and temperature for an ideal gas at a fixed volume, or a tank level measurement um, versus a weight measurement, a scale. To detect a fault, then you look for a deviation from the model. Then you calculate that as y minus f of x. That should be zero if you're on the curve, because y is supposed to be the same as f of x. But it usually isn't exact because of measurement noise or more systematic errors like bias. So if you're far enough from this curve, you have detected a fault. So this is an example of adding redundancy to your system. You're introducing a second dissimilar sensor, but you're also introducing an extra equation to tie it to the others. The equation adds redundancy. This approach of looking at models and using them to link together variables and looking for deviations from the model, that generalizes quite well to much more complicated systems with a lot of variables and a lot of equations. The notation is essentially the same if you happen to know linear algebra. Y minus f of x should still equal zero, and it just doesn't. And you look at the calculations, and there are many, many different techniques for doing this. Don't need to get involved in those. But we'll say that these kinds of approaches are used in a lot of different places. Electrical power grids do this, people monitoring flow networks, pipelines, they all make use of linking together variables using equations. So, for instance, a lot of network kinds of approaches have the notion of a network node, where it's either, in the case of a flow network, a node represents a place where flows come in and go out, or in an electrical circuit, you have the Kirchhoff current law, where the sum of the currents in equals the sum of the currents out. So those provide you with a set of equations and a set of variables, and you can do your analysis looking for deviations from that model. Some models make predictions over time. For instance, the inertial guidance systems we talked about earlier. If we know the thrust of a rocket, we know its acceleration by Newton's law. And from that, we can predict its future velocity and position, given its current position and velocity, all done at regular time intervals. Now, we can use these models to detect faults conceptually the same way we've already talked about. We look at the actual measurement values and subtract the predicted value of those measurements. We look for consistently bad predictions, meaning high measurement corrections, especially with the same sign on average, meaning that we're usually predicting too high or too low. The implementation of these systems can be part of the normal state estimation system, which almost every spacecraft will have. State estimation means estimating the current position and orientation, and also the corresponding velocities and angular velocities. The point of the Kalman filter is to balance the model predictions at each time step with the measurements. So it's a two-step process where there's a prediction made using the model equations, followed by a correction to account for the new measurement values. And these are really tuned. They specify the level of the measurement noise for each sensor and also what's called process noise. Process noise is to account for uncertainty in the model that could be caused literally by things like local gravity variations, especially in lunar orbits where they really have that. In travel in the atmosphere here, wind gusts cause you to noise, or just plain inaccurate. Anyway, when the measurement corrections are consistently too high or too low, then we have detected a fault. There are approaches to fault detection that are based mainly on data rather than on models. Cluster analysis can be used. It's especially useful when there are large numbers of sensors and careful modeling is too hard or time consuming. The values of a lot of sensor or other derived values are stored as a case, each represented as a dot in the sample pictured here. The plot here just shows two variables called x1 and x2, but many more would be used and available for display. The variables might be something simple, like a temperature and a pressure, but usually they're calculated variables that result in clear groupings of the cases. The idea is that normal operating modes, as well as various operations under faults, result in clusters of data for each operating mode. After experience, these clusters can be labeled. If the individual cases can be labeled ahead of time as normal or with some particular fault, that's called supervised learning. If they aren't labeled, the clustering can still be done. But the first thing that people might want to do is to start to at least label the normal operations for fault detection purposes. And they can leave the other clusters unidentified, at least initially. That can be enough to be useful. For instance, General Electric monitors a lot of variables for their jet engines over their entire lifetime. These are the engines installed on planes with cooperative customers. It also includes gas turbines used in pipelines and so on. And this includes numerous vibration measurements in different directions and locations, numerous temperatures, fuel flows, turbine speeds, and so on. Now, some of their failure modes grow over a period of time. For instance, a pebble might chip part of a turbine blade, and this leads to some vibration due to the unbalanced rotation. And that vibration may eventually lead to some other small damage, pieces flying off of the blade, maybe some bearing wear, all of which does more damage, leading to more vibration, and the damage grows over time. Similar things can happen when hot spots occur. They develop in certain areas, and damage can kind of spread over time. Anyway, when operations drift away from a normal operating cluster, it may be time to refurbish or retire the engine before a fault cascades into a catastrophic failure. This is useful even if the actual root cause is unknown. This particular example isn't really real time, like our other diagnostic examples, and it may be handled by a maintenance department rather than an operations organization. But it does illustrate the principle. This particular use has been called condition-based maintenance also. By the way, when the clusters can be labeled with specific fault names, then the method supports fault diagnosis as well as detection, unlike a lot of the model-based approaches we just talked about, because they only model normal operation rather than including operation with faults. Now we look in more detail at fault diagnosis, that is, identifying the root cause rather than just detecting that we had a problem. In general, it's more difficult, and at least it may require different techniques as well. I brought this slide back up. We've shown it before, but I kind of want to kind of motivate the analysis here. Remember, in this example, we were just pumping some propellant from rocket storage to the rocket itself, and the measurements weren't in agreement. They differed. It looked like we might have lost some. We went from 100 down to 96. Now the question is that a leak? Is there a sensor problem? And if so, which one? Or maybe both? Or does that just fit within normal accuracy and variation for the flow or volume measurements that are done? It's this difficulty in sorting out sensor problems versus equipment problems that leads to a lot of trouble, and is why it's so difficult sometimes to actually do the diagnosis. Deviations from models of normal operation are really great for detecting the faults, even if you didn't think of all the possible faults. The model of normal operation might become wrong because of the fault. The model doesn't include things like leaks or shorts, parts falling off, explosions, and so on, but you'll still get a deviation from the model, even in the more extreme, rare kinds of events. So you will detect a fault. But your problem here is still just that detecting it doesn't tell you what the cause was, and as a result, it doesn't guide you in mitigating the problem or tell you what to fix. One approach to fault diagnosis is to model the abnormal operation. It's called an abnormal operation model. One of those approaches is cause and effect modeling of that abnormal operation. This is also called a fault propagation model. And there's an example here in the diagram to the lower left. In general, in these kind of diagrams, you may have the possible root causes on the left-hand side, and the right side of the diagram would have tests or measured observations one way or another. And then in between, there's a variety of intermediate conclusion kinds of things, some of which may be measured, some of them maybe not. But anyway, the general flow of cause and effect is from left to right. So, for instance, if you have an exhaust system leak in your car, you probably will have high oxygen in your exhaust system, as measured at your tailpipe. And there will be lots of other things that the exhaust system leak might also cause, but they're just not shown in this particular diagram. Similarly, if you have the fuel pump weak as a named fault, well, that'll cause a couple of things. Your fuel pressure gauge will start reading low, and your fuel system will get inadequate fuel. And if that happens, then in turn, moving to the right in the diagram, you'll lose some engine power. Now, you can read this diagram going the other way as well. If somebody measures the oxygen coming out of your tailpipe as having a high O2, you can say, well, what could cause that? And you look back to the left to find out. Well, one immediate possible cause is the exhaust system has a leak, but there's other possibilities too. You may have inadequate fuel going to your car, and as a result, there's too much oxygen coming out as well. So typically for any of these nodes, there's a whole variety of possible causes, and I've left a variety of open arrows there to indicate that. And similarly, for any root cause problem, it will have all kinds of implications. And again, many of them left off of this diagram. And this can be done in a little bit more abstract way. On the right-hand diagram here, we just labeled possible causes, root causes C1, 2, and 3, and then some various conclusions that come from that. Now, what are these nodes exactly? Well, the nodes represent conditions, and that includes failure modes, like the root causes, and it includes measurement observations, like outlet temperatures greater than 1200 degrees. But it could also be an observation like no response to a network ping. It could be basically a test result rather than necessarily something you observe all the time. You can think of this as kind of a logic diagram where true is bad. So if you imagine things lighting up in red indicating you have a fault or you have a problem, when you go true, that's what happens. You get the bad indication. And what you really try to do is, given a set of observed conditions, mostly toward the right-hand side of this diagram, you work your way back to the possible faults and figure out what they are. Now, in this particular example, the nodes pretty much represent OR conditions. You can think of them as OR logic. For instance, the fuel system inadequate fuel, it could be caused by a weak fuel pump or the fuel injectors being clogged or any number of other possibilities. In general, these nodes could be other kinds of gates like and. Typically, if you have say you have an emergency backup kind of a thing, if you're looking at a battery problem, then you'd have to have both the primary battery and the battery backup both fail before you'd lose power, and then all the things that would follow from that would only occur in that situation. It might even be a kind of a thing, almost like a majority voting logic kind of thing. M out of n things happen. That'll be bad enough to cause a particular problem. Now, the good thing about this kind of diagram is that you can use it tracing back from symptoms back to causes. You can find the possible root causes, but also once you've identified a root cause, one or more, you can then predict the impacts just going from right to left. So if you've identified, in fact, that the fuel pump is weak, then all of the downstream conclusions there moving to the right will be true. And so you can predict the impacts. We refer to this more abstract example in the lower right corner several times. So in this particular case, in prediction mode, you can say if you have root cause C1 happening, it's true, then that causes DNF to be true as well, and then subsequently H as well. Or if you're looking the other way during the diagnosis, you might say that if F occurred, you had evidence of that one way or another, then what are the possible causes of F? Well, it could be causes C1, C2, or C3. Let's run through an example of diagnosis with a model of this sort, the same abstract model we had before. Here we've got color coding on these diagrams to indicate the state, where the red colors indicate something is true, meaning there is a fault or a problem of some sort. Um, Yellow means you suspect there might be a problem, but there's multiple choices, so you're not sure what the problem is yet. The clear white here indicates you don't actually know. And as a side comment, in almost any kind of logic dealing with diagnosis, you have to have unknown as a possible state because there may be sensors that have failed, and maybe you can fix them, maybe you can't. But there may be long periods of time when they're not available, and you really can't know things. So you have to consider really three-valued logic: true, false, and unknown. Also, some of those may represent tests that you don't run on a regular basis, and you only run them when you need to help differentiate between a couple of different possible faults. So anyway, we're starting off in the initial state here. We're assuming everything is completely unknown. We don't have any data yet. Now, suppose that H, the next step here, is observed to be true. That is, in effect, we've absorbed the fault detection step inside each of these blocks. Each one represents typically a condition like a particular sensor greater than 1200 degrees, as we said before. So that, in fact, has been an example of fault detection buried in here as input to the diagnostic step. So H returned this bright red color indicating we actually observed it to be true, that we have such and such a problem. Now you look at this diagram, there's only one possible input to the thing. Now you have to make kind of a closed world assumption here that your diagram is complete. The only possible cause for that H being true is that F must be true as well, just because there are no other choices. So you've inferred that that's true. We color it a kind of a lighter color of pink to say that it's inferred or predicted. We didn't observe it directly, but based on our diagram, it's the only conclusion we can draw. Now, now what happens? Well, now that we know that F, probably has happened, what could have caused that? Well, you look back to its inputs, and there's three possibilities. Causes C1, C2, and C3 are all possible, and we don't know which one. Any one or multiple of those could, in fact, be a root cause problem here. We don't know yet. That's why we may run some tests, or we may just have to wait for some other data to come in. So the next step is, now suppose that data came in on I. Maybe we chose to run a test. Maybe we don't normally observe this variable, but we ran a test because we're trying to see, well, maybe we can prove that cause C3 is actually okay. And that was the case. It was observed that we don't have problem I. And again, the single input possibility said, well, okay, so G, apparently couldn't have been a problem either. We color that in a lighter green. And working your way backward, well, if that's true, C3 couldn't possibly be a root cause. It's been ruled out. So now we're down to just two possible root causes left, C1 and C2, still shown in the yellow. Now the next step, suppose we actually have direct measurements on C2, and suppose we observe that that particular cause is ruled out. We said it's false. Now if that's the case, now we already know that C3 was proven good, root cause C3, and now root cause C2 is the only possibility left explaining why F was a problem is it must have been root cause C1. And then once you've known that, you can say, well, okay, I can predict ahead, and I can say, oh, by the way, and I can predict that D must be true also. So from this relatively small model, you can draw all kinds of conclusions just with a few pieces of data. And note that they're interconnected. This is different than a typical fault tree analysis you do that came out of the nuclear industry. Those diagrams are kind of problematic in that they're all assumed to be trees, but what happens is you work your way from a cause down to all the things that could lead up to it. And the problem is there's really a lot of overlap between multiple trees, and you can end up doing a lot of extra diagnosis. It's much better to have all of the logic combined into one diagram. And that way, when you have common cause problems, all of that can fairly easily be determined. There's a concept used quite often in fault diagnosis called a fault signature, and it gets involved in a lot of the pattern analysis kinds of diagnosis. What you start off with is what's called a fault dictionary, where you make a big table, and one is shown in the lower right-hand corner of this diagram, where the rows of it correspond to particular faults. And here we use the same ones that we had in our previous diagram. Root causes C1, C2, and C3 are the faults, and those are rows in this table. The columns in that table are the observed symptoms. It could be measured conditions or test results and so on. So in this case, we had nodes D, F, G, H, and I. I put F and G in parentheses because they'll be there if they're measured. If they're not, or testable. If they're not available for test or measurement, you wouldn't include them. So I threw them in here for completeness. So for instance, reading a row here for fault C1, If that occurs, then you can say that, well, D will occur, and so there's a 1 in the D column. F will occur, so there's a 1 for that. G will occur, or G will not occur, I'm sorry, so there's a 0 there. H will occur, and I will not occur. So that's a pattern. You can say it's a pattern of, for a given fault, what are the patterns of observable symptoms? And they're binary in this case. They could be numerical, but it's easiest to stick to binary. So, fault C2 is a little bit different. Fault C3 is different. The general idea is each fault hopefully has a unique fault signature. Now, if they don't, then you got some problems. That means you can't disambiguate. You can't tell for a given set of symptoms. You can't necessarily tell what your root cause is. You can only narrow it down to a couple possibilities. So, the row of the basically a row of this fault dictionary table, that is a fault signature. And you can generate this numerous ways. You might do it purely by data, kind of like we did before with clustering and so on. That's one possibility. Another one is to do some kind of analysis or simulation. So it could be kind of derived from first principles, or at least observed through simulations by causing the fault. And if the simulation could account for the fault, you can also fill out this table. So lots of different ways of filling it out, and that's why it's kind of a popular concept. The cause and effect models that we talked about can be used for generating these signatures, but you do lose some information when you do that. Basically, all that intermediate kind of causality is lost for predicting impacts. Once you have this table, you can't necessarily predict a lot of the impacts if you have other intermediate causes that don't even show up in the table. So that's a possible problem there. Biggest problem with these is that implicit in all of it, there's kind of a single fault assumption. Depends on the method. Some cases can be worked around. But the problem is, look at what happens for C1 or C3 as root causes. There is no single failure that matches all symptoms. If both C1 and C3 both fail, then you get a pattern that is different than any one than any one of the root causes that's in your table here. And a related problem is one of masking. In this example, suppose C1 occurs. Well, as a result, then D, F, and H are all true. That is, they're going to be the predicted problems. But that says that you can't even tell if C2 is failed or not. It's masked because the C1 totally obscures it. You could imagine going back to a car example. If you're doing some troubleshooting and the car won't start, you can't necessarily tell a lot of things because, say, the generator is not even running and so on. So these models can have problems, but the biggest single one is figuring out what to do if there are multiple failures. And as I said before, at any particular instant in time, two simultaneous failures probably won't happen. However, they might have occurred at different times, especially on a long mission. Some sensor might have failed or some fault might have occurred. It may be unfixable and it may go on for years. So you have to allow for the possibility of having them. But nonetheless, it is such a convenient representation that an awful lot of times you are going to be dealing with a fault signature. During diagnosis, what you do is you find out, well, what are the values for all of the variables that are columns of the fault dictionary? That is, get symptoms for everything. And then hopefully you'll have a signature that matches one of those rows. It might not. What do you do then? Well, for instance, we have an example signature right down here. We said, okay, suppose we measure that in this lower right-hand side of the slide here. Suppose we measure that D1 happened and H happened. If you look at that, in fact, look over at the cause and effect diagram. It might be easier to visualize, but you came out with the binary numbers. You got two symptoms, D and H are ones, the rest of them are zeros. You can calculate a distance to any row of that table, and distance could be almost any version. The easiest way to look at these are just to count the number of entries that are different. So for instance, cause 1, how close is that to the observed example signature? Well, actually, only one thing is different. Basically, F was observed to be 0 in the example and 1 for fault 1.
But the others, you're farther away from it. So that in terms of distance, you are the closest to cause C1. So probably you would pick that as the most likely fault out of all the faults that are known in your fault dictionary. So this binary fault signature approach, that's something that you can go through pretty quickly just with brute force. If you want to say, I have an example signature, I want to compare it to every one of the possible faults. If you only have a couple hundred or even a couple thousand, you could probably run through a direct comparison to every single element in that table pretty quickly. If it gets to be really big, you might want to consider some way of generating automatic decision trees or something. But this is an example in general of pattern recognition, and that was just a particular form of pattern matching. More generally, especially if your observations are noisy, you might want to go back more to the numerical variables themselves that are ultimately generating these observations and just run through a whole lot of cases. Use your favorite pattern matching tool to match patterns of symptoms to faults. You might use neural nets, for example. Lots of people do that sort of thing. Other approaches, you can also use rule engines. They're not so popular these days, but for a while, people, including NASA, were using them on a regular basis. And what you do is you go back to these kinds of diagrams like we showed before with the cause and effect, and you might choose to do what's called a compiled version, which essentially is like the fault signature, where you say, I just really consider the ultimate root causes and the measured outcomes. So, for instance, I might say, if D and F and H all happened, then conclude that it was fault C1. So you're basically change that into a rule. That's kind of a compiled form because again you're throwing away the direct causality information. Now you could do this in a more fine-grained way. You could actually essentially turn each one of these nodes individually into an if-then rule, and you can state it, in terms of going forward or going backwards. Either way, those approaches aren't as popular anymore, with the one exception being logic diagrams just directly implementing what we call forward chaining, that is, going um, from a set of symptoms, just directly inferring the causes through a logic diagram. So lots of different ways of doing the pattern recognition. There are some general problems to deal with if you're working with these models of abnormal conditions or even just patterns of data representing abnormal conditions without the models. One problem is what if a fault occurs that hasn't been explicitly modeled? Your problem then is the observed symptoms won't match any of the data or models either way. And you'll end up with either no conclusion or you'll get a nearest guess to the wrong conclusion. Um, Neither outcome is terribly good, but you're probably better off with no conclusion. The other problem is the diagnosing of multiple simultaneous faults. Some of these methods may fail badly. It just depends on the method. That single fault assumption is a common one, but as we said before, it's wrong for long lived missions where failures can't be fixed quickly or even fixed at all. For more information about fault detection and diagnosis, there's a link given below for further information. Next, we'll give a brief review of some examples of aerospace fault management failures. Two in particular, the Hakuto-R lunar lander crash, and also some Airbus and Boeing sensor failures, which led to crashes. And these were associated with the airspeed and altimeter measurements, which are tied together. These are both reviewed in a different video, the one specifically examining the Hakuto-R lunar landing. This was a craft developed by the ispace Corporation in Japan, a private company that was landing on the moon. And unfortunately, it crashed. This was really a failure in the overall fault management process. It wasn't due to a failure of a sensor. It wasn't due to a software bug. It was really basically kind of an engineering problem or an organizational problem. And we'll go into what that means. They have topography of the moon, and this is one of them. This is the path. The white line is the path that's followed, except, of course, it's above that. So you come along. If you were following the path in, the craft would go up a little bit, and then, of course, there'd be a big drop off, and you'd finally land in the crater. And that's what they're showing here. So, what were the events? They were flying along the crater wall, or before the crater wall. All of a sudden, they came up over the rim, And then, lo and behold, well, the altimeter, which is, they didn't specify what their sensor is. I don't know if it's a laser or radar base, but whatever it is, it rapidly changed. Well, no kidding. They just flew over a crater. Of course, it's all of a sudden, here they thought they were going to be 80 feet from a landing. All of a sudden, there's another 3,000 feet in there. And what did they conclude? They concluded it must be a faulty altimeter. They didn't think about this, or they wouldn't have done what they did. Anyway, there was a big deviation, so they threw it away. They just said, okay, well, let's not use that. It's no good. And the problem is they didn't have any backup for that. They didn't think through, well, okay, if you really don't have an altimeter, how do you land? I mean, this is a lunar lander. It better be good at it. And it turns out you really can't do it. So every one of these spacecraft would have a state estimator, keeping track of, well, where am I? Your position in space and your orientation. Sort of really 6 different variables there, as well as velocities associated with that. And, well, as soon as they said, okay, this altimeter is no good, let's just back up and say, well, let's use our last good value and then just go from there with inertial navigation. And that's apparently what they did. So they thought that they were actually still pretty close to land as a result.
We show in the more detailed Hakuto-R video how inertial navigation will drift too much unless there are altitude updates using the altimeter or other substitute data. So, this craft was doomed to a failed landing once the lone altimeter failed with no backup. The altimeter is a sensor. It didn't fail in the Hakuto-R case, but the problem was that the incorrect fault detection logic declared that the altimeter did fail. With no backup instrumentation, that guaranteed failure to land successfully. The crash was more dramatic than expected because it thought it was just a small number of meters above the ground when it was really 3,000 meters above the ground. So as the craft descended, it soon reached its final strategy of just dropping 1 meter per second until landing. So it was dropping 1 meter per second while still there were 3,000 meters between it and the ground. It just ran out of fuel and finally crashed. The crash proved that fault management was inadequate. First, the design failed. There wasn't enough redundancy in the sensors, or even a substitute using topographical information from a camera observation. As a result, they failed in fault detection and diagnosis. They concluded that the altimeter was bad when in fact it was correct. They also failed, especially in not designing fault detection and diagnosis for cases they would encounter, which included landing or even encountering a crater. They failed in fault mitigation because they didn't realize that inertial navigation would drift too much and could not correct for a huge error in altitude caused by not accounting for the crater depth. They couldn't do that unless they had the altimeter measurement. The control system, adjusting thrust to land softly, was really doomed.
But there's another lesson in there that people have to learn over and over again, that all these failure criteria, if you're going to say, well, this sensor failed, it's based on what? Well, it's based on something like rate of change. You say, well, okay, physically, some devices just can't change their thing. Like the spacecraft itself, it couldn't change its position that fast. It can't, just based on this mass and the thrusts that are available to it. So, and if you think about that, well, that's reasonable. So you could say, okay, well, things can't change that much. But then they forgot that, well, the land underneath them, that can change arbitrarily fast. You can be going over a vertical cliff, and that's, an infinite change. And so physics can be used to estimate some of the parameters, saying, okay, I know things can't change faster than X, but they can't control the topography. If they were doing other things, or if they were absolutely sure that they were never going to hit a crater, they could use a criteria like that. Okay, now by the way, though, it's easy to get smug and think, oh, only ispace has these problems. Nope, not at all the case. Every industry has these kind of problems. And it's a tough problem because you're detecting sensor failures, and you have to distinguish those from actual other equipment faults, and that's actually half the battle right there. And that's true whether you're talking about doing this with a computer or just even have people make these kind of decisions. Either way, it comes out the same. And aerospace is no exception. They're just as bad at this, maybe worse in some cases. In particular, not having enough sensors and not enough analysis on all the possible failure modes. And I'll cite aircraft as a good example. And you have 3 instruments that are kind of standard. You have an airspeed indicator, and it's shown in this picture over here. You have a vertical speed indicator, how fast are you going up or down, and an altimeter telling you the height. And we're talking about some of the same instrumentation here. These just are the analog gauges, but that's what you're sensing. And you need to know how fast you're going typically, as well as your height. And you use what's called a pitot tube to estimate that. So that's this little thing down here, the little red area in the lower corner of that picture, lower left corner. So the way you do that is you have something that's called a static port. It's just basically open to the atmosphere, where it's really just reading atmospheric pressure. So that could be inside an unpressurized part of your airplane, or typically just somewhere sticking on the side of the plane. And then the other port is called the ram port, which is facing forward and is exposed to the full force of the air hitting it. So there's a dynamic pressure there. They just look at the difference in the pressure between the two. And then from that, you can actually estimate your airspeed. It's actually a pretty straightforward kind of process. You can do it in a dial, or you can do it with calculations. There are some failure modes for this kind of a system where one port or the other gets blocked. So for instance, you might get ice, and it might block the ram air port where the fast air is, or it might block the static port. And you have different effects from that. If you block the ram air, then if you change your velocity, you don't notice it. If you block the static port, actually that affects not only the airspeed indicator, but it also affects your vertical speed and your altimeter. All of a sudden, that's not going to change much. And if it's partially blocked, it'll just be changing slowly. So you can imagine you got all those same kind of tests you'd have to do here. One test might be, well, what if the altimeter just all of a sudden is flatlined? It doesn't change. Well, you got to say, well, what's flatlined? Because if you're an automatic pilot, it's probably controlling pretty well at altitude, but it might still vary. It has to vary a little bit for the controls to even work. It's not a trivial problem. Those kind of problems aren't always thought through, and they don't always put redundant sensors in. And that's killed people, literally, both from Boeing and Airbus customers. I know it happened in the case of an Airbus craft. It was an Air France flight out of Brazil, and it crashed pretty much because icing and failure to recognize what happened. They didn't know what altitude they were at. And actually, Boeing has had exactly the same problems. So it's even a well-known problem in aerospace, and still, in the case of Boeing recently, they didn't want to actually put in the extra sensors or even provide decent warnings and training to people about it. So it's really pretty common. They don't have the redundancy built in, and they don't have the logic to exploit redundancy if they have it. It's one or the other.
Other space-related videos or slide presentations by me are available at the link shown here. That includes a web page and also a list of videos at my YouTube channel, so you can view them or subscribe for notifications about future videos. These presentations are mostly made as part of the meetings of National Space Society's North Houston chapter, and the link to that is shown. Topics like these are presented as part of a monthly news segment, and there are also lots of other interesting speakers and open discussions. You can attend in person or online via Zoom. Come join us.